With the principles of equilibrium established, we now have all the mathematical tools that we need to go and attack some really important chemical systems that have implications throughout um, just the world in general. What we'll be talking about first are acids and bases. And acidic basic behavior has applications in environmental chemistry and biochemistry and biology. Just acids and bases are things that we just kind of can't get away from because they're often found in aqueous systems. And so that's where we start. So now that we have equilibrium and those tools established, let's start to look at some important systems like acids and bases. The thing that's different about these subsequent chapters is what we're going to be learning mostly is chemical behavior. All right. So once we identify the chemical behavior, once we learn these new things that we can look out for to write the chemistry down, to write the actual equation for the reaction down, then everything that we learned in the subsequent chapters kicks in, right? So all this stuff down here, math, how to do equilibrium problems, remembering how to do limiting reactant problems, those become the like after effects of identifying the chemistry. So the first step in a lot of problems and what we focus in on is what is the chemistry? What is the chemical reaction? What are the important things I have to know about the chemistry? And then from there you enact your mathematical principles. If you mess up this part, then all of this subsequent math that takes a while and that involves complicated manipulations, all of this is going to be wasted time. So I can't stress this enough. With these subsequent chapters and starting with this acid and base chapter, we need to make sure we can identify chemical behavior appropriately and then go from there. In the context of acids and bases, one thing that we're going to stress, and I'm just going to preview it a bit now, is that sometimes we have to do limiting reactant problems like we did last semester. We have to do limiting reactant problems with things that we're going to call strong species, all right? Strong acids and strong bases, okay? These species, right, have a K that's so big that we say that there isn't really like a calculable K, all right? The reaction just progresses to products fully. All right. So now think about this just from what I was saying before. What if we identify the chemical behavior and we identify it incorrectly? What if we're supposed to get a strong species? That means, hey, we do a problem like we did last semester and we take the reaction fully to completion, right? But what if we misidentify? What if it's really not a strong species and we do this math? All of this math is going to be wrong, okay? And again, I'm going to reinforce this as we go through, but just to kind of give you a preview of what's coming. Equilibrium, okay? So when do we have to do equilibrium work? Well, remember, we just got done a chapter talking about equilibrium. Equilibrium occurs for weak species, all right? Weak species. And weak species have a calculable K. There's a K that's given. And so guess what we're going to be doing with these weak species? We're going to be doing ice tables, all right? So it's a completely different mathematical process depending on the chemistry, right? And like I said, I'm going to reinforce this again and again. I'm going to talk about the mathematical implications of strong and weak as we go forward. But again, this is just a preview to kind of set you up with some ideas that have to be in your head from the start. I need to have the chemistry correct to know the correct math to do. Strong species, we do a problem like last semester, like limiting reactant problems where everything goes to the product side. Weak species are associated with equilibrium problems like we were just done, or like we just got done learning, okay? So with this fundamental just sort of idea established of what the next few chapters are going to be like, and specifically what this acids and base chapter is going to be like, all right? Let's focus in on some definitions and let's talk about what an acid is. So let's do acid definition, all right? Now, the type of definition that we're going to actually enact, it fits with your other acid definitions that you know. This particular definition is called a Bronsted-Lowry acid. Earlier in the semester, we saw Lewis acids. Last semester, we saw Arrhenius acids. They all identify acids in the same way. The nice thing about Bronsted-Lowry acid and its definition is that it's really general. And what you do for Bronsted-Lowry acids, identifying something as an acid, is you look for something that's giving up an H+. So what we say about Bronsted-Lowry acids is that they are H+ donors. They're a species that is going to give away an H plus, right? Within the context of Bronsted-Lowry definitions, let's talk about bases. So what's a base definition? Well, for a Bronsted-Lowry base, right, what we would say is that we get a general definition where Bronsted-Lowry bases are H plus acceptors. This is different than earlier in the semester where we had Lewis acids and bases where we were following electrons. Here it's all about H pluses. Okay, so quick little example. Right. Bronsted-Lowry acids and bases. Right. Let's take a look at something like HCl plus NaOH. We know this reaction from last semester. HCl, hydrochloric acid plus sodium hydroxide. This gives you, all right, fully with one arrow, and we'll talk about how we can figure it out later, H2O liquid and NaCl aqueous. So let's kind of think about what had to happen on this side, right? On this side, we have an H here. And again, we kind of use that idea of Arrhenius acid. We look for H's out in front to identify where we have acids. Here's this H. Over here with this species, we have an OH. And we know that a neutralization occurred and we got water. So somehow the H and the OH, they must be attaching to each other for the reaction to progress. Well, let's take a look at HCl. If you look at HCl, what it had to do to make water, it had to donate its H plus. It's getting rid of its H plus. Right, Cl is now going to be associated with, not really because it's aqueous, but in terms of the chemical reaction, it's associated with sodium now. It gave away its H plus. So then that means that this is a Bronsted-Lowry acid. Well, where did that H plus go? It attached the OH minus to make HOH, which we call water. So OH minus accepted the H plus, and that means that this is a Bronsted-Lowry base. Now, this is a general definition that kind of fits with our other definitions that we saw before. Again, for an Arrhenius situation, something that starts with H as an acid, it's the same definition. It's going to give us the same ideas. It's just a little bit more general. NaOH, which is part of a hydroxide family. We told you last semester that those were bases. It still fits, but now we can see why. We're watching what the H plus does, right? For one other example, that's not a full reaction, not a strong reaction, but a weak interaction. Let's take a look at acetic acid. Which can react with water, and we can establish an equilibrium. I'm going to write it down here. We can establish an equilibrium with H3O plus and C2H3O2 minus, which is aqueous. If I look on this side of the reaction, okay, so this is the reaction of like what acetic acid does when it's in water, right? Acetic acid in water, right? Well, on this side I see, oh, I've made H3O plus. So let's follow the chemistry and let's see which must have happened. This H here must have attached itself to H2O. And when it attaches to H2O, we get H3O plus, which is known as the hydronium ion. All right. So that means, following our Bronsted-Lowry definition, HC2H3O2, it gave away its H plus. An H plus donor, that's a Bronsted-Lowry acid, right? Well, what happened to that H plus? It went to a different species. The species it went to is H2O. Well, H2O is an H plus acceptor, if we follow the H plus. So H2O is an H plus acceptor, so we signify that as a base, all right? So if we can see that Bronsted-Lowry definition, okay? Follow the H. If something's getting rid of an H, okay, then it's an acid. If something's gaining an H, then it's a base. Now, take a look at the reverse reaction. So this reaction is a little bit different than the HCl NaOH reaction we just looked at. For this reverse reaction, guess what? We also have an exchange of an H. If you look here, to go from the products to the reactants, remember this is double arrow, so not just going in the forward direction, but going in the reverse direction. Looking at this, well, wait a second. Here's C2H3O2 with a negative, and it kind of wants an H plus. It has a spot for an H plus because it has this negative sign. So what can happen to go in this direction is, well, I have to get H2O. So one of these H's to go in the opposite direction must leave this. This species must donate its H to C2H3O2 to make HC2H3O2 on the reactant side. So if we follow this reaction this way, we can see this donation must occur. So this H3O plus on this side of the reaction is an acid. Where did that H plus go? Follow it again. It's going to attach itself here to generate this species. So if it's attaching itself here, it's a base, all right? Now these species on the right-hand side, we call them special types of acids and bases. We're going to call those conjugate acids and conjugate bases. And so whenever you see that C dot, that stands for conjugate. So let's get those definitions down. And they're sort of definitions. They're just ways to identify conjugate acids and conjugate bases. All right. So how are you going to do this identification of conjugate acids and conjugate bases? It looks like a conjugate acid is a starting base with an extra H plus. All right, a starting base with an extra H plus. It looks like our starting water base with an extra H plus. For every base, there's a conjugate acid on the other side. So what's a conjugate base? This doesn't look like a good S, sorry. There we go. So what's a conjugate base? A conjugate base is a starting structure or starting acid minus an H plus, or with an H plus missing. A starting acid minus an H plus. So here's a starting acid. What does its conjugate base look like? Remove the H plus. Oh, its conjugate base is right here. Now, identifying these parts of an acid-base reaction are incredibly important because remember, way back from the beginning of this video, we have to know what the chemical behavior is. And conjugate acids have acidic behavior, and conjugate bases have basic behavior. And we have to understand that when we get into the more complicated problems of this chapter. All right. One more example quickly. Just to identify acids, bases, and conjugates, because those are common types of problems that you'll see. Let's take a look at NH3, aqueous. Let's take a look at aqueous ammonia. NH3, when it's placed in water, undergoes the following reaction. When it's placed in water, what we get generated on the right-hand side with an equilibrium is NH4 plus and OH minus. All right, so this is a very important reaction for us. All right, so pause the video, see yourself now. Can you identify the acid, the base, and the conjugate acid and the conjugate base? So hopefully you're able to look at this reaction and say, let's take a look at NH3. What did NH3 do? Well, its structure changed into NH4 plus. Well, how does it go from this to this? Well, the only way for it to go from this to this is this picked up, all right, an H plus. It accepted an H plus. And when a species accepts an H plus, it's a base. That means right away over here, this NH4 plus, this looks like a starting base with an extra H plus, that means that this species right here is the conjugate acid. H2O then, all right, what happened to H2O? Well, H2O became OH minus. So it gave up an H plus, it lost an H plus, and if it donates an H plus, it's an acid, right? That means over here, the structure that looks like it, but it's missing an H plus, oh yeah, I just wrote that definition down, or that way to identify it down. If I have a starting acid and it looks like we're missing an H plus, a starting acid minus an H plus, okay, this is a conjugate base on this side, all right? This leads to important ideas associated with weak species, all right? So like I said, identifying acids, bases, and conjugates. Acids and bases are always on the left-hand side. Conjugates are always on the right-hand side. Look for adding an H plus to get the conjugate acid. Look for losing an H plus to get the conjugate base. I know I mentioned this before. Real quick, sorry, one last thing here. Whenever I write OH minus, I keep the minus there. If you want to write it over here, you can. The reason I write the minus is because it's on the O. The reason I write it there, okay? And you'll just see me do that throughout the video, so get used to it. You don't have to write it there, and you'll see some books write it as OH with the minus there. It's just a personal preference to remind me that, oh yeah, the negative is on the O, right? So back to general ideas for weak species. Once we can identify something as a weak acid, so for weak acids, there is one type of chemistry that you'll see, and it's a chemistry that we actually kind of saw with the example that was 2 examples ago. For weak acids, you're going to be given a K. And remember, we are associating that word weak with an equilibrium problem. And we know that equilibrium problems require a K. We call these Ks Kas. What does the A stand for? Acid, right? So for weak acids, you'll see it Ka given in the problem, or you'll be able to look it up in a table. The chemistry is the same every single time, right? If I have a general acid, HA, aqueous, all right? If I want to show it acting like an acid every single time, if I have a weak acid, the other reactant from your acid is water. And if it's a weak species with a Ka, an equilibrium is established. And what you generate every single time is hydronium ion for these weak acid interactions and the conjugate base. Acid plus water gives hydronium and the conjugate base. This is one of those times in class where I repeat it like 4 different times to make sure it's like stuck in your head. But you can just kind of loop back in the video if you really want to hear me say it over and over again. But honestly, this is incredibly important. As soon as you see you have a Ka, you know it's a weak species. Acid plus water gives me hydronium, which is the conjugate acid, right? And A minus, which is the conjugate base, right? A is just a stand-in for any sort of counter ion, okay? So in our previous examples, remember, we kind of use just general symbols sometimes to represent, sort of similar chemical behavior, like common weak acids are things like HF. So in this case, when I write a reaction with HF, look how it fits this form, all right? And even go back in acetic acid and look at how you would write the reaction for acetic acid. If I give you HF, which is a weak acid, and I said, show me how it acts like an acid in water. React it with water. Generate hydronium ion. What's A minus in this case? Well, look at what the counter ion is to the H. It's F. And one more example just to make sure you understand that this is a general reaction. Again, look at your acetic acid example, but we can do something more complicated like HClO2. This is a weak acid. So if it's a weak acid, what do? We react it with water. We generate the hydronium ion. And so what's the counter ion here? The counter ion here is going to be ClO2 minus. Acid plus water gives me hydronium, which is the conjugate acid, right? Your base plus an H plus is the conjugate acid, and the conjugate base is your original acid minus an H plus, right? So hopefully you can see with these two examples what this means. And it's the same for any weak acid where you'll be given a Ka, okay? This is how we write the chemistry. This is the first step that we need to then go on and do the math associated with these problems. Similarly, when we have weak bases, so for weak bases, and I start with the weak stuff because we're just got done doing equilibrium. So we're comfortable there, we're ready to go with equilibrium. For weak bases, we know they're weak because we have a K that we can calculate. It's not too big, it's something I can look up in a table or is given to me in a problem. We have these Ks called KBs. Now for any general base, which I'm just going to use the symbol B for, the way that you show it, acting like a base in water, is you take that base, you react it with water, and what you get out is the conjugate acid, where the base picked up the H plus. It has this extra charge now, because it not only picked up the H, it picked up an H plus, an extra charge. And then you generate OH minus. So our basic species generate OH minus as the conjugate base of H2O, right? Go back and look at our ammonia example. It fits this perfectly, okay? Another base, let's just take a look at like CH2, NH2, right? Oh, sorry, CH3NH2. So CH3NH2, if I say, hey, here's CH3NH2, it's a weak base. You know that because here's a KB, right? The chemistry for any base reaction is you take your base and you react it with water. You heard that right. We react both our acids and bases when we're using a Ka or a Kb. Water is the other reactant. What we're going to get out is our conjugate species here. Now I'm going to write it a little bit differently just to kind of show you how it's written, right? The H kind of can go in different spots, right? I'm going to write this as CH3NH3 plus. The base picks up an H plus, right? And that new structure that's generated is a conjugate acid of our original structure. And then OH minus is always the other product when you're talking about your base reactions. Now, if you would write this instead of CH3NH3 plus, I just want to show you because in Chem 101 and other textbooks, the H really goes to the N here, all right? The C is kind of full. The N has that lone pair on it, right, to actually pick up the H plus. So this is really the correct way of writing it. If for me you wrote it as HCH3 NH2 plus, I would technically accept that. But again, because you're going to see this form again where we have these N's that pick up extra H pluses, because that's where the lone pair is, it's good to know this form as well. But again, kind of look at this general form that you see here. All right, the base plus water gives you the conjugate acid and OH minus. Whenever you're using a KB, this same process follows. Base plus water gives me conjugate acid and OH minus. These Kas and Kbs, do we use them when we have weak acids and bases? So a lot to digest, but again, really important to digest this because you're not going to be expected just to be able to write this chemistry. Now there's a K associated with this, so what can we do? We can build an ICE table underneath and analyze from there. And we'll eventually talk about that later on in this week, right? See what you can get out of this video. Watch it again if you have to. As always, come up with questions, send them off to me, all right? And let me know any issues you're having.